So this is the idea of the algorithm called Quicksort. So it's very likely that many of you have heard of Quicksort before, but it's also very likely that many of you have been confused by Quicksort before. So I find Quicksort to be a very interesting algorithm for a number of reasons. And I really like to prompt the idea of Quicksort by thinking about how it relates to merge sort. So with merge sort, we had a constant time split, right? We just split in half. And then we did the recursive calls on merge sort, using merge sort on these halves. And then we had a linear time merge. So in Quicksort, we have something somewhat different. And we swap the complexities of the split and the merge. But then the recursive piece stays the same. So in Quicksort, what we do is first we split the array into two pieces. Split array in two pieces. So I'll call them D and E. Two pieces D and E. I won't have a guarantee that they're the same size, but what I want to guarantee is that everything in D is less than or equal to everything in in E. So I'll split the array into two pieces D and E such that for all I in J, D of I is less than or equal to E of J. Right? And this is just a way of saying everything in D is less than anything in E. Okay, so this is our split. And so, the question here is what's the complexity of this, right? How fast could we do this split, which we'll address in a moment. Then what we'll do is we'll quicksort both halves, and I shouldn't say halves. I should say we'll quicksort both pieces. Quicksort both pieces. Okay, and this will have some recurrence relation that'll be associated with it. We can't necessarily say it's 2t of n over 2 because we don't necessarily have a guarantee that the two pieces are the same size, but we'll address that in a moment. Quicksort both pieces, and then 3, we'll recombine the two pieces, the two halves, if they have been sorted, right, which is what quicksort ought to do in the recursive piece in step 2. If they have been sorted, then it takes 0 effort at all to combine them, right? So then we combine sorted pieces. And we can combine the sorted pieces without doing anything, right? Either with a bulk copies into an output array, or if we're able to do this thing in place just by leaving them as is, right? Because of this property, because when we initially split our array into two pieces, we guaranteed that everything in one piece was less than everything in the other piece. Okay, so this no matter what happens, this is at most a constant time operation, maybe even a 0 time operation. Okay, so here this is the idea of quicksort, right? So let's think about how we would do this. And I'm going to use the term, I'm going to stop using the term split, and I'm going to start using the term partition. Right, so rather than split, I'm going to say partition, which is it's the classical algorithmic way of describing what we're going to try to do with quicksort. So here is a picture of what quicksort does. And this is an example of how you can make incredibly compact pseudocode using the right kinds of algorithmic ideas. So quicksort does this, and quicksort is an in-place sorting algorithm. So we don't have to worry about 0 to n. We're just going to say we have some array somewhere in memory, and quicksort has indices for that array. So quicksort will operate on particular indices. So suppose we have an array and we're looking at the indices from L up to R in this array. Here's what we're going to do. First, we're going to say if these indices are different, right, which means that this array has more than one element in it. So if L is less than R, right, and what this means is literally this means if they are different, right? So here's my comment. Here I'll use red for comment. If different, there it is. If different. Then what we have is we have a partition function that we'll call, and I'll describe the way the partition function works in just a moment. So I'll set an index s, so this is going to be some index in my array, is equal to the output of the partition function. Partition. So what the partition function does is it just takes the entire array and processes it somehow, and then returns an index that we'll call the partition index, or the S for split index. So it takes the array, LR. Okay, so don't worry about what partition is doing. It's rearranging stuff, right? It's doing something to the array, and it's putting all the small things on one side and all the large things on the other side, and then it's returning the middle one. So it's returning the index where it made the split. Okay, so that's what partition is doing. Okay, and so then what we'll do is we'll call quicksort on everything to the left of S, and then we'll call quicksort on everything to the right of S, and then we're done. Quicksort A from the left index all the way up to S minus 1. Okay, that's everything to the left of S. And then we'll call quicksort on A on everything to the right of S. So S plus 1 all the way up to R. Okay. So this is a little bit confusing, right? You don't see any sorting happening here. You see a bunch of recursive calls. You see this partition thing. And the question is kind of what's going on? What's the recursion base case even, right? We don't even have an else on this if statement. But it turns out this is all that's necessary. So let's think about, in the next video, let's think about what the partition function is doing and how it can be implemented, and think about how that gets us a sorted array. But just to recap the idea here, what quicksort is trying to do is it's trying to come up with a way of splitting the array into two pieces so that everything in the left piece is small in some sense, and everything on the right piece is large in some sense. And it's the partition function that's doing that. Right? So the partition function takes the entire array, picks a number, and then puts that number somewhere in such a way that everything on the left of that number, and then arranges the elements such that everything on the left of the element of that number is small, and everything on the right of that number is large. So let's think about how we could actually implement this partition thing.